Okay, so good morning, everyone. Thanks, organizers, for having me here and for putting this really nice conference. So what I want to talk about is about the so-called Almeida-Thouless line and how this transition, we have evidence to show that this transition disappears below 6 dimensions. So this work was done in collaboration with Professor Mike Moore from the University of Manchester and with a PhD student, Bharadwaj. And so the work that I'm going to describe is mainly based on the second paper, which is this archive, which is up on archive recently and which is under review with PhysRev E, but also we will dip into some aspects from a previous work which was published a little bit earlier. Okay, so the nature of the spin glass phase, despite several decades of research, is still controversial. So there are two main theories which are posited. One of them is the so-called replica symmetry breaking theory, for which Giorgio Parisi won the Nobel Prize. And so this is the theory which was shown to be exact in the infinite temperature limit in the so-called Sherrington-Kirkpatrick model, but also in a range of models which lie inside the mean field universality class. But a competing theory is the so-called droplet picture. There are a few other pictures as well, but for the purpose of this talk, I'm going to focus on these two main candidates. And as a striking feature which one can use to distinguish between these two is whether or not there is the so-called Almeida-Thouless line. So the Almeida-Thouless line is a line of phase transitions in the magnetic field temperature phase diagram, which separates this high temperature, high field paramagnetic phase where you have replica symmetry with respect to the low temperature, low field spin glass phase where the claim is that there is replica symmetry is broken here, as opposed to this, the droplet picture says that there would be no, there's no spin glass phase if a magnetic field is turned on. And so there are lots of studies which have been done also for realistic nearest neighbor models, three-dimensional models, and so on, where there's people have said one way or the other in both directions, and also lots of simulation studies, but also experimental works have proved to be not. It's not a settled issue. So Mike Moore and co-workers have argued, right, using a bunch of theoretical arguments. So there are works by Bray and Moore, then there is works by other papers in this domain in the last decade or so, which have tried to argue that D equal to 6 might be a critical direction, so a dimension below which actually the RSB should fail. And so we show data which seems to suggest that indeed there is evidence for this picture, and so therefore droplet model would hold, right? So this is an important open question, is whether whether RSB holds at all for the 3D nearest neighbor spin glasses, and more generally whether it holds for all dimensions D less than 6. And so in order to address this, a large number of studies have focused mainly on the Ising spin glass, where various variants of this Ising spin glass model have been studied. But so in this paper we argued, during my PhD, where we argued that in fact one can study a vector spin glass model, and turning on a magnetic field which is random in all the component directions gives us an AT line also for vector spin glasses. And so the advantage with studying, for example, Heisenberg spins instead of Ising spins is that you can study larger system sizes, because the equilibration is eased due to because of the continuous degrees of freedom, and then there are some very nice algorithms available which help equilibration. So even so, it's very challenging to directly work with a 3D model and then put in all these spins, and then system size tends to be a huge challenge. And so one clever workaround was used by Luisi et al. In 2008. So where they said, so first of all, an interesting model to study is the 1 over r to the sigma model, where you have the interactions which die off as a power law. And so by tuning this exponent sigma, you have access to a range of universality classes all the way from short range to infinite range. And Ducey et al. Argued that, okay, even doing this is quite expensive numerically. So instead what you do is you say that the probability that there is a bond between any two spins I and j, that dies off as 1 over Rij to the sigma. And when there is a bond, then you take it from the same effective strength. So with this method, you can fix the effective number of neighbors per spin to be some coordination number z, and therefore it is a much more numerically much easier to handle, and you can go to bigger system sizes and so on. So this is the model that I want to study, but with Heisenberg spins. I will show you some data. So so it has been shown that there is a correspondence between the exponent sigma and the effective dimension that it corresponds to. So one can, given d, one can go to sigma or in the other direction. And so yeah, so we will make use of this to make statements about the AT line itself. So the model itself is like here, you have Heisenberg spins. So you have Jij and Hi's are also drawn from this. So they're Gaussian random variables. So there is this, on average, there is a spherical symmetry. So you have, so the strength of these fields can be tuned in terms of these HRs. Whereas for these Jijs, like in a standard way, you pick them to be Gaussian random variables with mean 0 and standard deviation unity. So there is a whole way of generating these bonds and stuff which is technical. It's there in the papers if you're interested. So I mean, effectively, so you're working with a model where these couplings are something like this. But as you go from very sigma equal to 0 corresponds to the infinite temperature, infinite range model, namely the Sherrington-Kirkpatrick model, if there's no dilution, right? So, but if you can dilute it, is what we're saying. So you dilute it, and then you can study a range of these sigmas. As you increase sigma, you'll see that I mean, although the effective number of bonds for any spin is the same, you see that more longer range bonds are more common when you're at sigma equal to 0, but they become more and more short range as you go to higher values. And so, this proxy model is a useful model to study. And in particular, so if the critical dimension, below which if RSB were to vanish, so the corresponding sigma would be sigma c equal to 2/3, right? So between sigma equal to 2/3 and sigma equal to half is the so-called mean field regime. And so all the data that I'm going to present to you is like large scale numerics performed in this regime within the infinite, within the mean field regime, right? So, so of course, so like I just said, so computationally it's efficient to work with this kind of a model. You can go to much larger system sizes. And so like I said, okay, so this is some details. I'll just quickly flash some data and then I will stop. So this is like the standard quantities which one studies: spin gas susceptibility, correlation length. And so this is the technicalities of how to do this, how to study the system size dependence. So then you see that at sigma equal to 0.6, you have a way of studying it for different different quantities. And then you can also fix the temperature and then study in the other direction, which is an innovation of our own. And so this AT line, there is an approximate expression that you can write down analytically, and then the data seems to sit on it. For sigma equal to 0.6, 0.63, we have more data. 0.64, we have more data. 0.65, we have more data. So we are focusing on this regime between 0.6 and 0.67. We collect all this data and then meticulously tabulate it. And then, so yeah, so the main message from our work is actually right here. So there is this approximate expression you can write down for the AT line. And so there is this coefficient A of sigma, which we write down these values of A of, we compute it numerically and then plot it as a function of sigma. And then we see that essentially this seems to be going down to 0. This coefficient itself has a tendency to fall off to 0 as you approach 2/3. And therefore, we argue that with the aid of large scale Monte Carlo simulations, which basically ran for like 100 years because of CPU time or something, which seems to suggest that A of sigma goes to 0 as sigma approaches 2/3, and thus presenting evidence that the AT transition disappears below 6 dimensions. Thank you.
Okay, since there are no questions, we can thank the speaker once again. It's nice.
Thank you.